We're beginning our discussion of probability. This is going to be just part one. We're going to talk about basic calculations of relative frequencies. This is what normally you would think of is the actual probability calculation. Some basic laws and facts, and a little about what's the difference between probability and statistics. Now we're going to start off with an example in which we are talking about Larry Bird of the Boston Celtics basketball team. In the particular game, he took 53 shots and made 47 of them. Based on that performance, what is the probability of Larry Bird making any particular shot? Now, if we are talking about probability, and actually I'll talk a little bit more generally just about relative frequency. Most people have a pretty good intuitive sense of, in this particular example, well, it's going to be 47 over 53. If we were to write that out in words, we could write it as favorable outcomes, in other words, making the basket, over total number of outcomes, his 53 total shots. So, relative frequency, in this case, would be 47 over 53, which, if we did this as a decimal number, would be 0.887. Or as a percentage, that of course would be 88.7%. Some vocabulary here. When you're asked for probability, usually you give it as relative frequency. So if the question is what's the probability, it'd be 0.887. If you're asked what's the chance of him getting it, usually chance implies percentage format, and so you would say 88.7% chance of it happening. Now, I'm going to go and refer to something we're not going to talk about in this video, somewhere else. But we're looking at this as just total number of shots taken over total number of shots, or scored versus taken. Now, you could also very easily say, well, wouldn't the probability of making a shot depend on the distance from the basket? And intuitively, you would think, yeah, probably would. Well, that's going to be a good example of two variable statistics that we're going to talk about in another section. But I'm bringing it up because you can frame the question in a lot of different ways. And the answer really depends on how the question is framed. So here, we actually are asked, what's the probability of Larry Bird making any particular shot? Now, really, this 47 made shots out of 53 taken shots is in one particular game. Would the performance in one game necessarily be exactly the same in all games? Well, no, not necessarily. Of course, Larry Bird is professional. The difference between his games is probably not huge, but certainly younger players, their statistics, their probabilities would change. You would hope. Hopefully, it would get better with experience. And so, really, this is the probability of him making shots during that one game. You could, again, with Larry Bird, if it's late in his career, say, well, it's probably not going to change too much from game to game. Or you could collect more data. You could, instead of doing 47 from one game, do a whole bunch of games, right, and seeing what the overall average is. And then you would maybe be a little bit closer, which brings up one of the first laws of probability. And that first law is the law of large numbers. The law of large numbers says, as the sample size increases, the relative frequency approaches the theoretical, also known as the actual value. And the Larry Bird example is a good one. You have that one game, and that gives you a relative frequency. If you increase your sample size and start averaging over multiple games and even career, it's going to start approaching this sort of theoretical or actual value. Now, with something like making basketball shots, the theoretical or actual value is a bit of a moving target because it depends on someone's skill. If we start talking about flipping coins or rolling dice or these sorts of activities, there is in fact a theoretical value that we'll talk about in a little while that we do actually can calculate. And if you flip a set of 5 coins, you won't necessarily get the theoretical value for the number of heads showing. But if you keep doing it time and time and time and time again, it will start approaching that theoretical value. Now with basketballs, it can be reduced to simply making the shot or not. But sometimes it gets a little bit more complicated. There might be more possible outcomes. And so we need to talk about a very important vocabulary term, which is sample space. And what sample space means, the collection of all possible outcomes. Not the probabilities of them, just what are they? What are all of the possible outcomes? And then once we know that, we can start figuring out the probabilities of each possible outcome. A good example of this is the dartboard, right? Where if you throw, a dart, there's lots of different possibilities here, and you can break up the possibilities in a number of different ways. You could say, all right, there are lots of different numbers, these sort of pie pieces. What's the probability of hitting any one particular pie piece? There are concentric rings, of course, the bullseye, and these concentric rings. What's the probability of hitting those particular rings? If we take that as our example, right, if we want to figure out the concentric rings, what would be our sample space? Well, how many concentric rings are there? I mean, we have the bullseye in the middle. Right, we have this ring, third ring, this is the fourth, fifth, sixth, and I guess you could come out here to be the seventh, and I suppose there is the possibility of missing the board completely, and really you have 8 possible outcomes of concentric circles. So the question might be, how would you actually write out the sample space for the dartboard? Well, you could do something like this, which is a nice indication or an introduction for notation. Right? This would read the probability of outcome 1 as we have diagrammed on the dartboard itself, that's getting the bullseye, and the probability for getting the dart in any of those 8 different regions. And these are all the possibilities. That's the important part of sample space, is that there is no possibility we have not included. No matter what happens, the dart will go in one of these 8 regions, and so there's going to be a probability for each region. Now, unlike a coin or a die or something like that, the probabilities will not be the same. We have these very skinny circles, we have the wider circles. So that's going to be a little bit more complicated in terms of a theoretical calculation. But if we wanted to get an experimental calculation, of course, we could just have a big long game of darts and do our ratio of successful outcomes or favorable outcomes is what I used before. Over total number of really trials, and I could even be more specific. Number of times you made it into the bullseye over the total number of throws, and number 2 would be number of times you hit the second concentric circle over the total number of throws, and so on. And you can just do it. You just have a big long game of darts and keep track. And then you could do different days and see if you're improving in certain areas and all that kind of fun stuff. So this is simply sample space. Now, once we know sample space, the next important rule about probability, the sum of all probabilities in the sample space always equals 1. As a relative frequency, of course, 1 is 100% as a percentage, which, if you think about it, should hopefully make some sense. If we go back here and say, well, if these are all the possible outcomes, then when you add them up, it should equal 100%. If it doesn't, then you haven't included a possibility. So we actually use this quite a bit in calculating. So now, we've gone through a couple of, that's the law of large numbers. There we go. Sum of all probabilities equals 1. Now, what we want to do as a final topic, probability versus statistics. Now, I'm going to break this up a little bit. We have descriptive stats. And really what descriptive stats comes down to, with descriptive stats, being able to describe center, shape, and spread of any data set. And you really don't need probability to do that. Right? These are just calculations, and you can describe a data set very nicely. In probability, studying probability allows you to make a statement about what might occur when samples are drawn from a known population. From our basketball example with Larry Bird, if I were to say in the next 300 shots he takes, how many will he make? Then based on the relative frequency, you can just do relative frequency times 300. And out of those 300 shots, he would make, whatever that comes out to be. Now, are you absolutely certain he will make that number? No. All right, that's the whole might is very important in there. Probability won't give you a definitive number, but essentially a close guess. Right? And when you're dealing with probability, you just have to start getting used to a certain fuzziness, that you don't know specific outcomes. You don't know what will happen. You're just guessing at what might happen and hopefully making it as good a guess as possible. Now, with this, you actually don't need a whole lot of descriptive stats. Relative frequency, I showed you just a few moments ago. You just count number of successful outcomes or favorable outcomes over the total number of outcomes, shots made over shots taken. That doesn't require a whole lot of statistics, any shape, center, spread, no standard deviation. We certainly will start doing that, and actually start doing that soon when we start talking about probability distributions. But at the moment, it's a very simple relative frequency calculation, not a lot of statistics. Now, what we're going to be doing is tying these two together in what's known as inferential statistics. And this is where things get really fun, actually. Because inferential statistics is being able to make inferences, which is a fancy word for guesses, really, about an unknown population, when all that is known are sample statistics. So this is where we spend a fair amount of time later in the course, because it pulls together both the descriptive stats and the probability. Because now we don't know what the population is. This is some really classic survey kind of information. You want to know the height of adult males in country. Well, it's really hard to go around and measure the height of every single male in that population. So you simply don't have that population statistic. You can get samples. You can grab, 50 adults over here, 50 adults over there, measure samples, and then from those samples, infer what the actual population statistic will be, or, of course, could be. And that's where the probability part comes in, because you're making a guess what it might be based on known probability distributions. And so that really ties, inferential statistics really ties together the descriptive stats and the probability.